Welcome to Complexity Made Simple. My name is Paul Allen, and the subject of today's newsletter, well, we're going to take a look at the most common phrase I hear in all of my Six Sigma clients. And this phrase is when I teach them about how to get a process under control, how to get a process to work perfectly and as well as it can possibly be. The biggest comment I get is, there's nothing we can do. The raw material is coming in with lots of difference and there's nothing we can do. So we're going to use that little comment, we're going to concentrate on it. I'm going to show you a little theoretical scenario where a company would go, there's nothing we could do. And then I'm going to show you the role of statistics and variability control and their role in making the process better or worse. Variability is the key, and I want to show you your role in variability control, and then there's lots that you can do. So here's the subject of today's video. It's this comment. There's nothing we can do. And that would be the most common phrase that I hear in all levels of organizations when I tell them that we're going to get their processes to work better and we can do better than they're currently doing. They usually say, our raw material is natural and there's nothing we can do. Our raw material is coming in with too much variability. There's nothing we can do. So the example we're going to use, I'm going to just create a little theoretical example of two steelworks. Okay, so the two steelworks are having to dig up and purchase iron ore from somewhere around the world. Okay, so of course it's natural material. So this would be a common cry. This is the worst that it could potentially get. So here we go. There's nothing we can do. The raw material is natural. They throw their arms up and they don't try to improve. Okay, so we have two steelworks. So here we go. First of all, let's put a big hole somewhere in the world, and this is where, let's put a truck here. This is where some kind of big truck is taking something like that, maybe. He's taking iron ore out the ground, and then of course what they're doing is they're putting the iron ore on a ship and they're sending it across the world to the two steelworks. So here are the ships laden with iron ore, several of them coming across the world, and they're coming across to two piles of iron ore in them. Okay, and away they come. They're coming across the world to two steelworks. Okay, now I'm not going to attempt to draw the steelworks, but we'll call this Site A, and we'll call this Site B, and we'll say that this is the blast. So this is the iron making part of the process, and of course one of the inputs to this process is the ore. Okay, so now of course the iron ore has got variability in it. Now one of the sites happens to have the purchasing manager for the iron ore, for the world supply of iron ore to this particular organization. So this particular organization will say that it's company A, site A, they have the purchasing manager here who buys the iron ore. So what he does, he gets the iron ore to be tested. What's in it? And then what he does, he redirects what he considers to be the best iron ore to his site. Okay, so obviously what's going to happen here is the iron ore would naturally be variable. What this fine gentleman is doing, he's cutting out maybe the middle, sending the middle there to site A, the outer part goes to site B, and site B of course see more variability potentially than site A, and they react accordingly to that. And what they tend to do of course is they tend to make adjustments. So they're making crazy adjustments here. These people here have got standard settings because they're getting the material that they want. And what does site A do? If I talk to them and I say, we can do better, and they say, there's nothing we can do. We're being shafted by the supply of iron ore. Now at this point, I'm going to bring in some concepts of statistics, because this is the point where we need to talk about statistics, the power of statistics, and why you need statistics in your business life always. Okay, now some people think I'm obsessed with statistics. I read crazy books like this, like The History of Statistics, a book that I really enjoy reading, to be honest. I read these things so that you don't have to necessarily. But anyway, you should be obsessed with statistics too. Why should you be obsessed with statistics? Well, it goes like this. You see, every number you look at, every number in life, whether it's in business or in the newspapers, on the television, every number you see is an estimate. It's an estimate. And that's why you have to have statistics in your life, because if you accept the fact that every number is an estimate, the next sensible question you would be asking is, how good an estimate is it? And statistics tells you that. And if you know it's a good estimate, you can act and react correctly. If you know it's a bad estimate, you can act and react correctly. Now, of course, people often say to me, now Paul, we measure every one, or we have a piece of mathematics, and mathematics isn't an estimate. Well, even mathematics is an estimate, because look, I agree. 2 and 2 equals 4. That's not an estimate, but that assumes that all maths is like that. The minute you get this is just pure mathematics. We're not talking about the fact that your measurement systems might have error in them. Pure mathematics. Look, 10 over 3, what do you get? Of course you get 3.33 recurring. What do you do next? You round up. The minute you round up, you create an estimate. Maths is full of numbers like that. So even mathematics, every number in mathematics is an estimate. Now, don't get me wrong, sometimes it's a damn good estimate. I'm not saying there's anything wrong. And if you round it off like that, nothing wrong with it. It's a good estimate. But the point is still made. Every number's an estimate, and one of the key things you've got to answer is it a good estimate? So let's go back to how 2 Steelworks for a moment, because they're not using statistics. You see, when they go, there's nothing we can do, what site B is doing, they believe the estimate. They believe the estimate that tells them what's in this boatload of iron ore. Okay, now then, let's have a look at this, because they shouldn't be believing the estimate. They should go and find out how accurate these numbers are. Because, and this is a bit of experience on my side, the problem with iron ore, it's granular. I mean, if you take a look at some photos, look, so I've got some photos here, you can see that when it's dug out of the ground, it is essentially a rock. Yeah, so it's pieces of rock that come out of the ground. Now that makes the iron ore very, very granular. Even when it's been prepared, look, you can see here on the picture on the right hand side, the iron ore's been prepped into little nuggets. But even this is very granular because it's pieces. You've got pieces of iron ore. Now the iron ore is natural. It was created by a, I don't know, it might have been created by a volcano or something like that. There are also, by the way, different types of iron ore. And the one thing I would say is that these sites should be using the same type of iron ore. If what they're doing is switching from type to type to type to type to type, all bets are off. That would be a stupid thing to do. They would never get control of their process if they keep switching from different types of iron ore rock. So we're going to assume that they are sticking to the same type of iron ore rock, but the rock is very granular. Now, what does that mean for the estimate? What does that mean for the estimate? Well, what granular material typically does, it creates a very poor estimate of the boatload that's being shipped over. Why does it do that? Well, what you tend to find is this. You've got pieces, some big, some little. And because they're granular and they're made naturally, they're not homogenized. So what's in them? What's in piece A, piece B, piece C, piece D is completely different. So if, for instance, let's say you had an impurity like silicon in the iron ore, and we'll just take one example. So if there's a certain amount of silicon in the sample, and there'll be different amounts in the different pieces. And that creates a huge problem for getting a good estimate of a boatload of iron ore. Because, and I've drawn this quite small, let's make this silicon a little bit bigger. So if this big piece here, which is almost, we'll suggest that it contains 50% silicon for a second. If this piece goes into the sample from this boatload, it's going to make the silicon look really, really high. It's going to create this data point here. Now that's an estimate, but it's an estimate based on these few pieces of rock that have come from the boat. Is it a good estimate? Well, actually, I don't know. And if inadvertently this piece doesn't get used, so in this case, this would make the silica look really high. Let's say this piece doesn't get used, doesn't get picked up in the sample. Some other pieces get picked up in the sample. Maybe that makes the result look really low. Now, what's the real result from the boat? Well, it's almost impossible to know. Because in order to get the real result from the boat, what they literally have to do is to crush all this down into small granular amounts, as small as they could. They then have to mix, let's say there's 450 tons in this boat, they'd have to mix all 450 tons up and homogenize it, and then take a sample out of it. And then, and only then, might it be a reasonable estimate of what's going on. But because it's very granular, what you typically find is if you sample out of that boat, if you sample and you take samples from here and then samples from here and then samples from here and samples from here, and then you tested it, you'd get completely different results. Now, one of the things they do is I'm assuming that they do, industries that have granular material, what they'll do is they'll try and randomly sample out of the granular material. They'll create one big pile on the floor, they will mix it up as much as they possibly can. And then they do something called, so if you're looking down on the pile here, they cone it, and then they quarter it, and they'll repeat that, and that's a mixing process. And eventually what they'll do is they'll take one of these quarters and they'll select a sample which may eventually be crushed up and be very granular, but it will be a very small sample, and it will be almost like a cupful of iron ore that represents the whole boat. Now, depending on which grains they picked up, which pieces of rock they picked up, how much of the impurities and the chemicals they contain, they will get an estimate. Is it a good estimate of what's on the boat? Well, what I would recommend that they do is they do an MSA and they try it, because whenever I've done granular material, and I've done lots of MSAs on granular material, the condition of bottom ash coming out of furnaces where they're trying to tip the bottom ash into into underground tips and things, into waste tips. They have to check what's in the bottom ash before they can put the material to landfill. They find that the variability of bottom ash is huge, and if they sample different portions of bottom ash out of a furnace, it's all over the place because it's granular, it's highly granular, and it's very natural the way it's got created. And that's exactly what you've got here. So here's the deal. This site, so how is it making the sites behave? Because what we've really got is this. The two sites are actually looking at very poor estimates of what's really going on. Site A believes it's winning because they believe their estimate. Site B believes it's losing because they believe their estimate. So how do the two sites behave? Well, they behave like this. You see, let's get rid of this guy. There's more inputs to the process than just the iron ore. And then when the iron comes out the other end and goes off to steel making, this is where, of course, more ingredients get added, because this is going in here and other ingredients are going in. So both of these are going to steel making. So let's talk about the behavior. One site thinks it's getting lots of difference. One site thinks it's getting lots of the same. I would contend they're both getting the same iron ore. They're both getting terrible estimates, bad guesses, and they're just picking the guesses that are in the middle, and therefore these think they're getting good material. So what do? Well, the thing that they do is nothing. You see, because they think this is consistent, the other ingredients, and I don't know what they might be, but the other ingredients that they could mess about with, they take their hands off because they don't feel the need to mess with those ingredients. So think about this for a second. Coming in here, in reality, is something that's varying a lot more than they can really see. So they think they've got some consistency, but it's actually varying a lot more than they can see. It's just one of 1, 2, 3, 4, 5, 6 ingredients. Now, because they think ingredient iron ore is consistent, they leave the other 5 alone. What's the total variability in their process? Just the iron ore. That's the only thing they've got. So of course, when they get the steel making results, They get consistency that's based on the fact that only the variability of the iron ore shows up in the final results. And here's where variability is so important, because what site B is about to do is make the whole situation a whole pile worse, because they think they've got variability here, when in fact, what have they got? They've actually got the same as site A. They just don't know it, because they don't know they've got a terrible estimate. So what do? Well, they take ingredients A, B, C, D and E and they play with it. They play with those ingredients to try and offset the variability in the iron ore. They play with A, they play with B, they play with C, they play with D and they play with E. Guess what they get? How many variables are moving in their process? Well, they have all 6 variables moving in their process. They can only ever look crap against the other site. What do they say when you say let's do something about it? There's nothing we can do, because they believe these estimates. They have estimates and they believe them. Now, why am I obsessed with statistics? Because my statistics are going to tell me how good my estimate is. And then what I'm going to do, I'm going to leave the process alone. This is self-inflicted, because you're moving 5 variables you don't need to move. What you're seeing here is a result of all 6 variables being moved, and most of it is self-inflicted because you don't understand your estimates. What would I do first? I'd do an MSA so that I can see how poor my estimates are. But very quickly, what can you do? Once you know that you cannot see what's happening, the only sensible thing to do is agree a standard recipe for your steel, take your hands off and fix everything. And then the only variability that comes out the end of the process is the variability from the iron ore. And that's the power of variability. That's the power of statistics. If you don't understand that every number you look at is an estimate and that you need statistical tools to help you to figure that out, if you don't understand the power of variability, you can't adjust variability away. You can only make it worse. You'll do what steel plant B is doing. They're swinging on the dials, thinking they're making it better, but they're making it worse. And when you say to them, can we do process improvement? They say, there's nothing we can do. Not only is there something that they can do, what they can do is cheap. It's cheap as chips. They just have to agree standards for A, B, C, D and E, fix them and use them, because that's what A's doing. And A's only doing it because they're being fooled as well by the fact that they think they're getting better material. That's the power of variability. That's the power of statistics. If you understand your estimates, you understand your process and you behave properly. Otherwise, you'll make the process worse. Understand your estimates and variability and make piles and piles of cash without any investment whatsoever. That's the power of variability.